Okay, this screencast is on the definition and basic idea behind what we call electric current. Okay, so electric current is defined as the rate at which charge flows past a given point of an electric circuit. Now, it's another rate quantity. We've dealt with a lot of rate quantities already. Power is a rate quantity. Uh, Velocity is a rate quantity. Acceleration is a rate quantity. Whenever you see the word rate, all it means mathematically speaking is we're going to take our quantity, some quantity, and divide by time. So it's going to be a ratio of some quantity to time. When you talk about electric current, we're talking about the flow, so current, like the current in a river, of electrons. And since each little electron carries some charge, 1.6 times 10 to the minus 19th coulombs, then we define electric current as the charge Q that flows past a given space per unit of time. So it's charge divided by time. Now the symbol is I. Now you might say, well, it's current, why don't we just call it C? We'd like to, but the coulomb is what we use to measure charge, and that's already a big C. So we would have current measured in coulombs. And that could get confusing pretty quickly. So the choice was made to go to the French word for current. So that starts with an I, and they chose French because both Coulomb and Ampere, two scientists who had a big input into early electricity, were French. So 1 ampere, and that is a person's name, is equal to or defined as 1 coulomb of charge passing a given point for 1 second in time. Typically when we're talking about charge moving through, we often talk about wire. So here's an idea of the fact that the wire is actually moving through this cross-sectional space here, this area, and then it comes out the other side. Now charge has to be conserved, so whatever charge goes into that space has to come out the other side unless there was some other path for it to break off. And that ratio of the charge that goes through that area to the time that it happens is known as the current. Okay, so what do we believe? Now, typically when we start asking you what do you believe, we're trying to get at the point that a lot of our initial thoughts about this are going to be wrong. So they're going to be misconceptions. Turns out all 5 of these are typical misconceptions. Those are things that as average people we think that's the way it should work. Turns out no, it's not the way it works at all. So we'll try to use some of the ideas we talked about before with electrostatics and potential difference to see if we can show that these are actually false. Okay, so when a battery no longer works, it's out of charge, it must be recharged before it can be used again. Well, in everyday language, oh sure, I need to recharge my battery. But it's not recharge. Okay, recharge would indicate we need to pump in electrons. That means we would need to pump in stuff. Now, when you charge your cell phone battery, you don't add in more stuff. Okay, it's not recharge, it's re-energize. So when electrons go from the positive to the negative terminal of the battery has to do work on them, and work is equal to the energy. So the battery gives the electrons energy, not charge, and then they use up that energy as they go around the circuit. So it's not recharge, even though it's common use of language. Okay, B, a battery can be a source of charge in a circuit. The charge flows originates in the battery. Well, that's also false. Okay, the charge is already in the circuit. The wires have electrons, the light bulbs have electrons, the motors have electrons, everything has electrons. Our batteries would have to be huge if they actually provided the mass, the electrons, to move around the circuit. So they don't provide the charge. Okay, again, they provide the energy. Okay, C, charge becomes used up as it flows to a circuit. Now, the amount of charge would be less. Keep in mind that charge is conserved from our electrostatic study. That means the charge has to stay the same. I talked about above in the picture that you can't have charge go in one end and then suddenly it can't come out the other. So it's not the charge that's used up. Again, as it goes through the battery, the electrons get energy, and then to go around the circuit they have to use up the energy. It's kind of like going through a toll road. At the beginning, you have a certain amount of money in your pocket. That's what you got from the battery. As you go around the toll road and hit the different toll booths, you have to give up some of your money to get through them. The electron gives up energy to get through resistors, light bulbs, motors, whatever is in the way. Uh, Once it finally gets back to the battery, it has no energy left. And then the job of the battery is to re-energize it, not to give it more charge. The charge never goes anywhere. F will actually talk about in the later episode here, but charge, actually, the electrons have a hard time moving through the circuit. As they try to move through the circuit, they're all kind of blocking atoms and electrons in their way. So what happens to them is they hit some of these blocking electrons, and then that means they have to change their direction, and then they come back again, and then they have to change their direction. So in the end, they actually move pretty slowly, less than 1 meter per second through the wire. We'll see later on why it is that when you turn a light on, bam, it turns on all the way across the room, even though the electrons themselves don't get there. And letter E goes right on back to the idea of B, where we said the battery provided the charge. Again, it's false. It's not the electric company that creates or sends us the electrons. Okay, they don't supply the electrons. They supply the energy that creates the electric field. The electrons then are already there in our homes. They're in the wires of our homes. They're in our light bulbs. They're in our motors, whatever it is we're going to turn on. The electric company provides the energy that makes them move. And again, that's where we get the word current. Like the flow of water in a river, it's a current. It has to move to be actually electric current. Okay, so that's our first idea. Notice the large number of misconceptions we all have coming into this. Make sure you fight your way through that. You'll get a better understanding if you don't just take the first word and say, oh yeah, I remember that, that must be right.